All right, welcome back to another calculus lecture. In today's lecture, what we're going to do is use the closed interval method that we learned last lecture to tackle a new class of problem that is typically referred to as applied optimization. So these are some of the more sort of involved problems in calculus. They kind of have a similar sort of feel as related rates problems in that there's a process you can go through to solve them, but they take a little bit of time. So what I want to do is outline that process and then work a few examples of these optimization problems to show you how we can use calculus to sort of figure out the answers to these interesting questions. So maybe let's go ahead and motivate this with just a quick example. So let's see, a wire of length L is to be bent into a rectangle. And what I want to know is what dimensions of the rectangle maximize the area. Okay, so this is the sort of first example that we'll go with, and the process for solving these problems is generally the same each time. So go ahead and write that down. Process for applied optimization problems. So the first sort of thing that you want to do is you want to think about what sort of geometric relationship do you have with the quantities you're trying to optimize. So here I have a wire of length L and I want to bend it into a rectangle. So the first thing that I want to do is find a formula for the quantity you want to optimize. So in our case, that formula is going to be, well, the area of a rectangle is just the length times the height. Okay, so we'll come back to that in a moment. The next thing that we want to do is once we have that that geometric formula, it's typically going to depend on multiple variables. So maybe I'll put that in parentheses, will typically depend on two or more parameters. So in the case of the area of a rectangle, the area depends on two parameters. It depends on the length and the width, okay? So the next thing that we want to do, because we don't really know how to deal with multiple variables, is to reduce our problem to a single variable. So we want to find a constraint in the problem to reduce the number of variables. And so in our case, we have that the perimeter of the rectangle, the length of wire that we're using, is fixed. It is a number, just L. And so 2x plus 2y, if that's the length, if x is the width and y is the height, or the length, then the perimeter is going to be 2 times the sum of those things. And so that's going to allow us to reduce. We can take that and put it into our first formula to reduce it to one variable. And then lastly, we want to apply the closed interval method to minimize or maximize, that is just to optimize, the desired quantity. And I know this seems very abstract at the moment, but I think it'll make much more sense when we start working this problem. So we get a geometric relationship for the quantity we want to optimize. We reduce the number of variables using some other constraint. And then once we have a function of one variable, we can apply calculus methods that we know, at least. We're only doing single variable calculus. We can apply our methods using the closed interval method. Okay, so let's go ahead and apply this to our example here. So step 1, we have that the area is equal to the length times the width, where L is length and W is width. And then I also know that capital L, the wire that I have, that's the perimeter of this rectangle. And so it's equal to 2L plus 2Y. So just the sum of the two sides. Think about it. That's what the perimeter of a rectangle is. Anyways, so now what I can do is I can write the area function as a function of a single variable. So it doesn't really matter which one I pick in this instance. Sometimes it's going to be more convenient to pick one variable over another for computational reasons, but here there's a nice symmetry, so it doesn't matter. We can just say that basically we can solve this for one variable, and we can say that W is 1/2 capital L minus 2 little l, which is just L over 2 minus little l. Okay, so all I've done is just subtract the 2L over and then divide by 2 to get W by itself. And so now I can take this expression for W as a function of L and plug it in for the L up here. So I have that A, which now is a function only of, not W, of L, that this is now equal to, well, L times, and then I put in my expression for W. So L, capital L over 2 minus little l. And then we can expand this out and we can say this is 1/2 capital L times little l minus L squared. And now I'm in a position where I can actually try to optimize this function to try and find where it's, I should have notated that was part 2. Now I can try and find where its maximum or minimum occurs. Well, I want to maximize the area, so I hope that this function has a maximum. So if I want to go ahead and apply the closed interval method, well, I need to think about what are the what's the interval that I'm working with. We call it a closed interval method, so I need to think about this interval. So the interval, and the interval that we're thinking about is all the values of little l that I'm allowed to substitute into this expression right here. So interval of valid L. Well, L certainly can't be negative. That doesn't really make sense for the problem. So we at least require it to be non-negative. And then if I think about how large L can be, well, I can't really, I have to, if I draw my little rectangle over here, then you can think about taking L to be all the way as much as capital L over 2. That is, I'm just making W equal to 0. Okay, so I can go all the way up to L over 2, capital L over 2. So now I need to find the critical point. So here's my interval. Now I need to find my critical points that lie in this interval. So we can do that fairly easily. We take the derivative with respect to L. This is going to be 1/2 capital L minus 2 times little l, and then I set that equal to 0. And now if I solve for that, then if I add the 2L over and then divide by 2, I get that little l should be equal to capital L over 4. Now, this tells me I have a critical point right here. We should do some sort of reasoning to say that this is a local max or a local min, and we know how to do that. We can use the first derivative test. So we come down here, make a little sign chart. Here's my L over 4. If I just plug in, well, I can just use these 2 points actually. There's no problem in doing that. So if I just plug in 0 and L over 2, then A of 0, well, if I plug in A equals 0, I'm going to get 0. I'm sorry, not a of 0, a prime of 0. So a prime of 0 is going to be L over 2. And then, which is positive, L over 2 is a positive number. And then I can plug in L over 2 for L right here, because this is the point I'm using. So if I plug in L over 2, then I get 1/2 L minus 2 times 1/2 L. And this is going to be, well, this is just 1/2 L minus L, so this is negative L over 2. And so I have a negative here. And now if I think about what the first derivative test tells me, I have an increasing and then I switch to decreasing. So L equals capital L over 4 is a local max by first derivative test. And if I plug in my other 2 points just to see what the area is at each of those, well, you can sort of see that the way that we've thought about these, that the area is just going to be 0. You have either the length is completely just half the total length of the wire, or the width is, half the total length of the wire. And in either case, the area is going to be 0. So what should we say? So the area is maximized by choosing L equals to capital L over 4. And if I think about what W must be, well, if I plug in L equals capital L over 4, and I plug that in right here, and then I solve for W, I get that W is also L over 4. That is, I maximize the area by making the rectangle a square. So area is maximized by making the rectangle a square. Which is sort of satisfying in a way, I think, that you optimize the area by making all the sides sort of the same thing. And in general, this actually happens. If you want to maximize the area of a triangle with a fixed perimeter, you make it an equilateral triangle, or same thing with a pentagon, or all these sorts of things. Okay, so there's one example. Let's go ahead and do another one. I'll try and do 3 examples. Hopefully the video won't be too long. No need to just continue doing this in purple either. Make the whole notes purple. So let's maybe ramp up the difficulty a little bit. So a cylindrical can, is to have volume 16 cubic, we'll say centimeters, we won't make it meters, that would be massive, 16 cubic centimeters. What dimensions minimize the materials needed to make the can? That is, what dimensions minimize the surface area, because the surface area directly corresponds to the materials required to make the can. Okay, so I've got a cylindrical can. All that I know is that I want its volume to be 16 cubic centimeters, and I want to know what dimensions of the cylindrical can, that is the radius of the circle and its height, those are the 2 parameters that govern the size of a can, what do those need to be in order to minimize the surface area? So let's go ahead and write this down. So what is the surface area of a can? Well, if I go over here and draw a little picture, so here's my can, and then draw a little dotted line. So you can see I have two circles here. And we'll say this is R and H. So the area of a circle, well, that's pi r squared, and I have two of them on top and on bottom. So 2 pi r squared. And then I need to think about what the sort of surface area of the vertical part is. Well, you can imagine taking like a toilet paper roll and cutting it down the middle and unfolding it. I'll try and illustrate this. You know, if you just took that can or that toilet paper roll and cut it down the middle and then unfolded it, then you would actually just have a rectangle. And the area of a rectangle is just the length here times the height. Well, we know the height, that's h, and the length here is just going to be the circumference of this circle. So the circumference is 2 pi r, and then I multiply by the height, h. Okay, well, there's my surface area. There's my geometric relationship for the quantity I want to optimize, and in our case, we want to minimize it. So what's another relationship that I can use to reduce this to one variable? Because currently it depends on both the radius and the height. Well, I know that the volume is fixed. It's fixed at 16 cubic centimeters. So I know that 16 is equal to, and now I need to think about what the volume of this can is. Well, the volume is the height times the area of this circle. So that's going to be pi r squared h. Okay? Now I can take this expression and substitute it into here. I need to solve for one of my variables, and here it's definitely easier to solve for h because otherwise we have to take a square root, and we really don't want to do that if possible. So I know that h, just divide by the pi r squared here, we get 16 over pi r squared. And now I can take this and make my surface area, the materials that I need, depend only on the radius. So s is now only a function of r. It's 2 pi r squared plus 2 pi r times 16 over pi r squared. And we can simplify that a little bit. It's 2 pi r squared plus, this is going to be 32 over, so the pi's cancel out, 16 times 2 is 32, and then r divided by r squared is just 1 over r. Okay, so there's my surface area. Now I need to think about what are the what's the interval that I'm working with that of the allowable values of r. Well, there's not really a sort of minimum or maximum value that r can take. Certainly I don't want to make r equal to 0 because then this is going to blow up to infinity. So interval of valid r is, so we don't want to use 0, and of course we don't really want to take a negative number either, so we'll do 0, and then, well, I guess we could take r going all the way up to infinity, couldn't we? I mean, the height would be, you know, you'd be gradually making just a sheet of paper that has infinite size, but you know, your radius can theoretically be as large as you want. So we're just going to do this over the entire real line, excluding 0 and the negative numbers. Okay, so here's my interval for valid r, and now I need to optimize this function over this interval. So how do we do that? I guess I should have put that up here. So let's compute the derivative. So s prime of r, differentiate here, I get 4 pi r. This is r to the negative 1, so when I apply the power rule, I'm going to get negative 32 over r squared. So the negative 1, I subtract 1 from the power to get negative 2, and that negative 1 comes down as a scalar right here. So now what I need to do is set this equal to 0 and see where are my critical points. Well, do a little bit of algebra. So let's see, 4 pi r is equal to 32 over r squared. If I multiply r squared over and then divide by 4 pi, this tells me that r cubed is equal to 32 divided by 4 is 8, and then I divided by pi as well. And now this tells me that when I take the cube root of r, I get that r is 2 over pi to the 1/3, or the cube root of pi. Same thing. Maybe let me write that bigger. There you go. That way you guys can actually see it. Okay, so there's my only critical point. I only had to check one thing. So now I should verify that this is in fact a local minimum, because that's what I want. I want to minimize the materials needed. So we go over here, we do our first derivative test. 2 over pi to the 1/3. And our test points, well, let's see. Pi to the 1/3, oh, I don't know. I actually don't know how big that is. I think it should be bigger than 1. So pretty sure 1 is less than that. Question mark. You can do that on a calculator if you're unsure. We'll see if I made a fool of myself here in a moment. And then 2 is certainly bigger than this because I'm taking 2 and dividing by a bigger number. So let's go ahead and compute the derivative at each of these points. So s prime of 1 is going to be 4 pi minus 32. Pi is like around 3, so this is going to be like 12 minus 32, so this is certainly negative. And if you don't believe me, you can put that in on a calculator, figure it out. And then if I plug in 2, I'm going to get 8 pi minus, we'll go ahead and write this down, s prime of 2 is 8 pi minus, let's see, 2 squared is 4, 32 minus, or 32 over 4 is 8, so this is minus 8. So this is like 8 times pi minus 1, which is certainly a positive number. And again, you can do this on a calculator. You don't need to do it by hand. I'm just, this is how I lecture. So now we think about what does the first derivative tell us about this critical point. So I'm decreasing, and then I switch to increasing. So I do in fact have a local minimum. So 2 over pi to the 1/3 is a local min by the first derivative test. And so it turns out that that's actually the point which is minimizing my surface area, right? This is the only point at which it can be minimized. So minimize materials, just phrase it in the way of the problem, minimize materials by taking r equal to 2 over pi to the 1/3. And then we should also figure out what h is. And in order to do that, we can use this expression. So we know that r and h are related this way. So if we just plug in this value for r, we should be able to get a value for h. So 16 equals pi times 2 over pi to the 1/3 squared times h. And so h should be equal to, well, 2 squared is just 4. So then 16 divided by 4 is 4. And then I have a pi times a pi to the negative 2/3. So this is a pi to the negative 1/3 because we're dividing by it. And then we square it, so it's pi to the negative 2/3. And then I have 1 minus 2/3, so this is going to be pi to the 1/3. But then that's multiplying by h, so I have to divide by it. So to the negative 1/3. And I verbally described that, but you could certainly do some more algebra steps to figure out what that is. Okay, so here's my radius, here's my height, and I've minimized my surface area now. We're done. So we're done. Sometimes you sort of need to realize when you're actually finished in a problem to see that you've actually sort of gotten to the right answer. Okay, so video is already at about 25 minutes. I don't want to make this go on too long. I may upload another video that just works another example or so. Maybe we'll just do 2 lectures on this. I don't know. We'll see how I feel. But anyways, with that being said, we're coming to the conclusion of the section of applying the derivative to various different problems. And we've got one more topic to cover with the derivative, and after that we're going to move into the second half of the course, which is integral calculus, which is some cool stuff in and of itself. All right, so see you all in the next lecture.